Good morning everybody. I am Dr. Ravi M. Medahalli, Professor and Head of the Department of E&CE, SZ Balikundri Institute of Technology. In today's lecture I am going to give lecture on the semiconductor diodes. Friends, as you know that the P-type and N-type semiconductors, if they are taken separately, they are of limited usage, that is application. If you join a piece of P-type material to a piece of N-type material such that the crystal structure remains continuous at the boundary, a PN junction is formed. The diode is a two-terminal semiconductor device. Like a resistor, the diode has two terminals. However, unlike resistor, the semiconductor diode has a nonlinear current voltage characteristics. A PN junction cannot be produced by simply pushing two pieces together or by welding, because it gives rise to discontinuities across the crystal structure. Special fabrication techniques are adapted to form a PN junction. The semiconductor diode can function as rectifier in case of the high current diodes, switching devices, right, in case of the low current devices. Also it can be used as the voltage regulator, that is for Zener diode, and other than that it has got plenty of applications that we shall see later. A PN junction is a device formed by joining P-type with a N-type semiconductors and separated by a thin junction called as PN junction diode. Here we have got a P-type of silicon, right. On the right side we have got N-type of silicon, and the terminal connected to the P-type, that is the called as anode, and the terminal connected to the cathode, the N-type silicon, is called as the cathode. The majority carriers in P-type silicon are electrons, whereas the majority charge carriers in N-type silicon are holes. Let us have a look at the graphic symbol of PN junction diode. This arrowhead indicates the conventional direction of the current flow when the diode is forward bias. The P side of the diode is always positive terminal for forward bias and is termed as anode. The N side is called the cathode, is the negative terminal when the device is forward biased. If you look into the VI characteristics of the ideal diode, for the diode behaves like an open circuit for V less than equal to 0, that is which corresponds to I equal to 0. So therefore, right, in the case of the reverse bias, right, you can see this is the characteristic what we are getting for an ideal diode. For when it is forward bias, ideal diode behaves like a closed switch, that is for I for a V equal to 0, I will be greater than 0. So that is what you can see over here. So the conducting in one direction and not in the other is called as the VI characteristics of the diode. The forward biasing voltage makes it turn on, reverse biasing voltage makes it turn off. Let us see how a depletion layer is formed in semiconductor diode. That is when there are no external connection, no battery is connected. The excess electrons in the N region cross the junction and combine with the excess holes in the P region. The N region loses its electrons, becomes positively charged. Similarly, the P region, when it accepts the electrons, becomes negatively charged. At one point of time, the migratory action is stopped. And additional electrons from the N region are repelled by the net negative charge of the P region. Similarly, an additional holes from the P region are repelled by the net positive charge of the N region. The net results in a creation of thin layer of each side of the junction, which is depleted, that is emptied of mobile charge carriers, and this is known as the depletion layer. The thickness of the depletion layer is in the order of 10⁻⁻⁶ meters. The depletion layer contains no free and mobile charge carriers, but only fixed and immobile ions. The width of the depletion layer depends mainly on the doping level. If both the layers, P and N layers, are heavily doped, then it results in a thin depletion layer. If both are lightly doped, that results in a thick depletion layer. Now let us see what is potential barrier. The electrons in the N region have to climb the potential hill in order to reach the P region. The electrons trying to cross the N region to P region experience a retarding field of the battery and therefore repelled. Similarly, for the holes from P region, the potential thus produced is called as potential barrier. The value of the potential barrier in case of germanium, it is 0.3 volts, whereas it is 0.7 volts in case of the silicon. Here this particular slide shows the P region on the left side, consisting of the holes as the majority charge carriers, whereas on the right side we have N layer with the free electrons as the majority carriers. In between this P and N, you can see this, the depletion region, as I defined, the region that is depleted of the free charge carriers is called as the depletion region, and due to this depletion region, a barrier is established. So that can be seen over here. Now the PN junction can basically work in two modes. That is when battery is connected to the diode. That is first is the forward bias mode, and the second one is the mode is called as the reverse bias mode. Whenever the positive terminal of the battery is connected to the P region and negative terminal of the battery is connected to the N region, it is called as the diode will be in the forward bias mode. If the negative terminal of the battery is connected to the P region and positive terminal to the N region, then the semiconductor diode will be in reverse bias mode. Let us look into the details of the forward bias PN junction. So here you can see that, we have got a PN semiconductor diode with a P on the left side, whereas the N on the right side, and in between the P and N layers we have got a depletion region. And you can also it can be noted that the positive terminal of the battery, it is connected to the P layer, and whereas the negative terminal of the battery is connected to the N layer. So therefore the PN junction is said to be forward bias, and accordingly a barrier potential exists across the PN junction diode. And please note that in case of the forward bias, the applied battery voltage and the barrier potential will be act against each other. So in case of this forward bias PN junction, it forces whenever a positive terminal of the battery is connected to the P and a negative terminal of the battery is connected to the N type, then it forces majority charge carriers to move across the junction, decreasing the width of the depletion layer. This in turn decreases the built-in potential, that is called as barrier potential, and lowers the barrier height, and therefore the number of carriers will be able to diffuse across the barrier, and therefore the diffusion current increases. However, please note that the drift current remains same. The drift current is essentially constant as it is mainly dependent on the temperature. So therefore, when the semiconductor diode is forward bias, the current flows from the P to N. Here you can see this particular slide shows the PN junction when it is in the reverse bias mode. In this case, the negative terminal of the battery, it is connected to the P, whereas the positive terminal of the battery, it is connected to the N layer, and therefore in between this P and N layer you can see that a depletion layer exists, that is the layer containing the immobile ions, and therefore correspondingly we will have a potential barrier across the junction here. In case of the reverse bias p-n junction, right, the free electrons and free holes are attracted back towards the battery, because when the positive terminal of the battery is connected to the n type and negative terminal of the battery is connected to the p type of the semiconductor, the free electrons and free holes are attracted back towards the battery and hence back from the depletion layer. Therefore, the depletion layer grows, and this in turn increases the potential barrier and increases the barrier height. So, in turn this decreases the number of carrier which are able to diffuse across the barrier there. Hence, the diffusion current decreases, whereas the drift current remains same, and that means almost no current flows through the p-n semiconductor diode. Only a reverse leakage current called as IS, which is nothing but the drift current that will flow from N to P. Therefore, thus we can say that a reverse bias p-n junction does not conduct any current. Only the minority carriers cross the junction which constitute a very low reverse saturation current, and this reverse saturation current, it is in the order of microamperes. Friends, let us have a look at the VI characteristics of the semiconductor diode. You can see that, right, the V is along the x axis, whereas the I is along the y axis, and this it can be noted from this VI characteristics that this particular region has got three modes. One is forward bias mode, another is reverse bias mode, and whereas the third region is called as the breakdown region. The forward bias region is determined by V greater than 0. So, this is what you can see here. So, and whereas the reverse bias region, it is determined by minus VZK less than V less than 0. So, that is over here, and over here, and the breakdown region, it is defined by V that is less than VZK. So, that is what is you can see over here. So, finally, it can be noted from this VI characteristics that, right, there are three regions are there. One is forward bias region, right, defined by V greater than 0, then reverse bias region, that is defined by minus VZK less than V less than 0, and the breakdown region determined by V less than VZK. In forward bias, the p-n junction has turn-on voltage based on the built-in potential, that is called as barrier potential of the p-n junction. The turn-on voltage is typically in the range of 0.5 volts to 0.8 volts. In reverse bias, the p-n junction conducts essentially no current until a critical breakdown voltage is reached. The breakdown voltage can range from 1 volts to 100 volts. The breakdown mechanisms include avalanche and Zener tunneling. In case of semiconductor diode, whenever the semiconductor diode is in forward bias, no current flows until the barrier voltage, that is 0.3 volts for germanium, whereas 0.7 volts for the silicon is overcome, right. Then the curve has a linear rise and the current increases with increase in the forward voltage like an ordinary conductor. So, please note that the barrier voltage, it will be 0.3 volts for germanium, whereas it is 0.7 volts for the silicon. Once the forward voltage crosses or exceeds the 3 volts, the majority charge carriers passing the junction gain sufficient energy to knock out the valence electron and raise them to the conduction point. Therefore, the forward current increases very sharply. With a reverse bias, the potential barrier at the junction is increased. So, whenever the semiconductor diode is reverse bias, that is when the negative terminal of the battery is connected to the P type and positive terminal of the battery is connected to the N type, the semiconductor diode is reverse bias, and therefore, the potential barrier at the junction increases, and therefore the junction resistance increases, and which in turn prevents the current flow, that is through the semiconductor diode. However, the minority carriers are accelerated by the reverse voltage, resulting in a very small current called as reverse current, that is in the order of the microamperes. With the reverse bias, whenever the reverse voltage is increased beyond a value called breakdown voltage, the reverse current increases sharply and the diode shows almost zero resistance, and this is known as the avalanche breakdown. Reverse voltage above 25 volts, right, destroys the junction, PN junction, permanently there. So friends, you can see here a PN junction under forward bias condition. So it is defined by this particular equation, that is IV characteristic equation, wherein I is given by I is equal to Is into e raised to V by NVT minus 1. So you can it can be seen from this equation that there is an exponential relation exists, right, and also the relation between V and I, it is a non-linear one, where here you can note that it can be noted that the Is is called the saturation current, which strongly depends on the temperature, whereas the N, it is usually is equal to the 1 or 2. In general, it will be 1 is equal to 1, and also it can be noted that the Vt is the thermal voltage. The PN junction, when it is in the forward bias condition, it can be noted that, right, the a conduction diode has approximately a constant voltage drop across it, and it is called as the turn on voltage. This Vd on, the turn on voltage for that will be equal to 0.7 volts for silicon, whereas it is equal to 0.25 volts for the germanium. Diodes with the different current ratings will exhibit the turn on voltages at different currents. So therefore, finally you can note down that from this the VI characteristics, okay, there are three reasons of the three reasons. One is the forward bias mode, wherein which is defined by V greater than 0, and the reverse bias, which is defined by the minus VZK less than V equal to less than 0, and there is a one more reason called as the breakdown reason, which is determined by V less than VZK. Friends, now let us see some diode parameters over here. What are the different parameters of the semiconductor diode? There are 4 parameters. The one is called as the VR, the maximum reverse DC voltage that can be applied across the diode, whereas the second one is called as IR, that is called as the maximum current when diode is reverse bias with a DC voltage, and the third one is IF, the maximum average value of the rectified forward current, and the fourth one, it will be FM, the maximum operation or operating frequency of the diode here. If you look into this, the diode approximation, there are 3 approximations of a diodes are there. One is, you can see that either the diode is indicated by the open either by open circuit or closed circuit. In the second approximation of the diode, we have a switch, right, either in the open circuit condition or closed in series with 0.7 voltage drop. In third approximation, right, the semiconductor diode can be considered, right, equivalent circuit of the diode, right, can be indicated by a switch in series with the 0.7 volts battery, which is in series with the RB, that is called as the bulk resistance here. Depending on the application, the diode can be modeled in one of these 3 approximations. The first approximation of a diode is simply a switch. If the diode is forward bias, the switch is closed and the diode will behave as a conductor with a 0 ohm of the resistance. If the diode is reverse bias, the switch is open. The diode will behave as open with infinite resistance. So therefore, this could be shown in the first approximation of the diode, right. The semiconductor diode can be shown either as a closed switch or the open switch. So when the diode acts as a closed switch, it behaves like a conductor with a 0 ohm of resistance. When the semiconductor is represented as open switch, then it behaves like a open switch with a infinite resistance there. If you look into the second approximation of the diode, the second approximation requires 0.7 volts of forward bias to overcome the barrier potential. Therefore, in case of the forward bias, the diode is represented by a switch, okay, in series with a battery of 0.7 volts. When because when the semiconductor diode forward bias, 0.7 volts appears across the diode and current flows. Similarly, if you look into the reverse bias, whenever the diode is reverse bias, you can see that the diode can be represented by the open switch in series with the 0.7 volts battery, and therefore no current flow over here. In case of the third approximation, right, the third approximation includes both 0.7 volts barrier potential and the internal resistance of the diode, that is called as the bulk resistance. Therefore, right, when the semiconductor diode is forward bias, the diode is represented by a closed switch in series with 0.7 volts diode drop, the 0.7 volts the barrier potential, which is once again in series with the bulk resistance, that is represented by RB here. In case whenever the diode is the reverse bias, this diode is represented by open switch in series with 0.7 volts the battery, which is once again in series with the bulk resistance RB there. So now let us see when are the different approximations are used. The first approximation, that is wherein diode is represented, right, either by closed switch or the open switch. So because whenever the diode is forward bias, the diode acts as a closed switch. When the diode is reverse bias, it acts as an open switch, and this is called as the first approximation. This is mainly used in troubleshooting and also to test whether the diode is conducting or not here. Whereas in case of the second approximation, this particular second approximation, whereas in second approximation, as we have seen, the diode is represented by either open switch or closed switch in series with a 0.7 volts barrier potential. And whenever the diode is forward bias, so in second approximation, the diode is represented by the closed switch in series with the 0.7 the barrier potential. And this particular second approximation, right, it is being used whenever a more accurate determination of load current and load voltage is required. Whereas the third approximation, wherein there are once again two models are there. That is one, if you look into the equivalent circuit, so finally you can see that whenever the semiconductor diode is forward bias, it is represented by a closed switch in series with the 0.7 volts barrier potential, which is in turn in series with a bulk resistance called as RB, and therefore whereas whenever the semiconductor diode is reverse bias, it is represented as open switch in series with the 0.7 volts barrier potential, which is in series with the bulk resistance. And this third approximation, it is being used during original design of the diode circuit here. So therefore, if you look into the models, mainly models of the diode approximation, finally if I want to conclude out of this diode approximation, there are once again three approximations of the diode. In first approximation, diode, it is simply represented by a switch, either in the closed switch or it may be open switch, right. Whenever the semiconductor diode is the forward bias, it acts as a closed switch. Whenever semiconductor is reverse bias, it is represented by open switch. In second approximation, the semiconductor diode is represented by a switch in series with 0.7 voltage, that is barrier potential, that is a battery here. So once again here, semiconductor diode, whenever it is forward bias, it acts as a closed switch, which will be in series with 0.7 volts here. So whenever the semiconductor diode is reverse bias, it acts as an open switch, which is once again in series with 0.7 volts here. Whereas in third approximation of the diode, you can see that semiconductor diode, it acts as, right, it is represented by switch in series with 0.7 volts battery, which is in series with the bulk resistance RB. So therefore, once again here, whenever the diode is forward biased in third approximation, right, so it is represented by the closed switch in series with 0.7 volts barrier potential, that is represented by a battery in series with RB. If the diode is reverse bias, so therefore it is represented by open switch, okay, in series with 0.7 volts, okay, which is in turn in series with the RB here. So therefore here you can say that finally, so the first approximation, it is being mainly used to troubleshoot, that is to know that whether diode is conducting or not, whereas the second approximation of the semiconductor diode, it is being used whenever a more accurate determination of the load current and load voltage is required. Whereas the third approximation, it is being used during the original design of the diode circuit here. So finally here if you we have had a discussion with regard to, right, the mainly the what is PN junction, that is PN junction once again consists of a P type of type of silicon that is doped with either boron or aluminum, and with the N type of semiconductor, which is once again doped with the phosphorus, arsenic, right. So and which is separated by the thin junction, therefore it is called as a PN junction diode here. And graphically it is represented by a diode, and in this case please note that the arrowhead, it indicates the conventional direction of the current flow when the semiconductor diode is forward bias here. And also we had a discussion with regard to VI characteristics of the ideal diode, right. So here whenever the ideal diode is forward bias, it acts as a closed switch. So therefore in that case, so whenever V is equal to 0, I will be greater than 0, and that is represented by this axis. And similarly this ideal diode, it acts as an open circuit whenever the open circuit, and that is the corresponding equation is V is less than 0. For V less than 0, I will be 0, that is represented by, that is this line along the voltage axis here. And also we have seen how the depletion layer is formed, right. So you can see that, right, as I have told you that this depletion layer, it is mainly because of the whenever the no connection, battery connections are made, so excess electrons from the N region cross the junction and combine with the excess holes in the P region, and the N region loses its electrons, so it becomes positively charged, whereas P region accepts the electrons and it becomes negatively charged, and therefore at one point the migratory action, it is stopped here. And because of this, what happens, an additional electrons from N regions are repelled by the net negative charge of the P region. Similarly, addition holes from the P region are repelled by the net positive charge of the N region. So net result is that this results in the a thin layer of each side, that is of the junction, which is depleted in the sense that emptied of the mobile charge carriers. That because this depletion layer, this is known as the depletion layer, it only consists of fixed immovable ions here, and the thickness of this depletion layer, it is in the order of 10⁻⁻⁶ meter. And this depletion layer, once again, it depends upon what the doping level of the P layer as well as the N layer. If the doping level of the both P and N layers are heavily doped, then it results in a thin depletion layer. If it is both are lightly doped, then it results in a thick depletion layer. Therefore, so the width of the depletion layer depends upon the doping level of the P as well as this. and therefore this particular depletion layer right, gives rise to one more term called as potential barrier, and this barrier, right, it is being produced, right, this mainly, okay, the electrons in the N region have to climb this potential hill in order to reach the P region here. So electrons trying to cross from the N region to P region experience a retarding field of the battery and therefore repel. Similarly, so the holes, whenever they try to move from P region to N, they get repelled by this potential barrier, and this potential, right, barrier, it is 0.3 volts in case of the germanium, whereas it is 0.7 volts in case of the silicon here. So that's what you can see here. Okay, this consists of, right, the P region having the holes as the majority charge carriers, and this is the anode terminal, whereas this is the N layer having electrons as the majority carriers, and in between the P and N you can see that a depletion region is exists here. So depletion region, it consists of only fixed and immobile ions, and because of this depletion layer there will be a barrier voltage across the junction here. So, and also we have seen that there are two modes of operation of the diode. One is forward bias mode, another is reverse bias mode here. In case of the forward bias mode, so when the positive terminal of the battery is connected to the P region and negative terminal of the battery is connected to N region, the diode is said to be forward bias mode, whereas whenever the negative terminal of the battery is connected to the P region and positive terminal of the battery is connected to the N region, the semiconductor diode is said to be the reverse bias mode here. So that is what is we can see here. So here you can see that the positive terminal of the battery, it is connected to the, right, the P layer, whereas the negative terminal of the battery, it is connected to the N layer, and in between this P and N layer you can see that a depletion layer exists, that is the layer which is depleted of the free charge carriers. So it contains only the fixed immobile ions, and therefore because of this depletion layer you can see that what happens here. So whenever the PN junction is forward bias, so the electrons will be able to move across the junction, decreasing the width of the depletion layer. So therefore whenever this depletion layer decreases, you can see that accordingly the barrier potential decreases, and therefore the diffusion current increases, that which flows from P to N region, whereas however the drift current, it remains constant here. Whereas in the reverse bias junction we have seen in reverse bias junction, we have seen that in reverse bias PN junction, the negative terminal of the battery, it is connected to the P layer, whereas the positive terminal of the battery, it is connected to the, right, the N layer, and therefore what happens, so this battery, it will attract the holes from the P layer, and similarly it will attract the electrons from the N layer, and therefore the depletion region width increases, and due to the increase in the depletion layer, what happens, the barrier potential increases, and therefore the current that is flowing from P to N, which is due to the majority charge carrier, decreases, whereas the drift current, it remains that the same, because this drift current depends upon mainly the temperature here, and therefore in case of the reverse bias junction, so only minority carriers will be able to cross the junction, and which constitutes a very low reverse saturation current, and this reverse saturation current is in the range of the microamperes. So, and also we have seen the VI characteristics of a diode. It consists of three regions. One is forward bias region, another is the reverse bias region, and third is the breakdown region. So as you see seen here, right, it may be seen from this that the forward bias region, it is defined by V greater than 0. So you can see that until the forward voltage reaches the cut-in voltage or threshold voltage, right, so the diode cannot conduct, so the current will remain 0. Once it exceeds the threshold voltage, so what happens, there will be sharp rise in the current here. That is what you can see that in the forward bias region, whereas in the reverse bias region it is defined by minus VZK less than V less than 0, wherein the current is mainly due to the minority charge carriers, and it is in the range of microamperes, whereas the breakdown region, whenever the reverse voltage exceeds this the VZK, so there will be a breakdown, a large current will be flows through the junction diode here. So therefore you can see that the barrier potential or turn on voltage, or you can say that the threshold voltage, it varies from the material that is being used in case of in fabricating the PN junction diode. So in forward bias you can see that PN junction has a turn on voltage based on built-in potential of the PN junction. So therefore turn on voltage is typically in the range of 0.5 volts there. So it varies in the range of 0.5 volts to the 0.8 volts, whereas in the reverse bias the PN junction conducts essentially no current until a critical breakdown voltage is reached. The breakdown voltage can range from 1 volts to 100 volts, and this breakdown mechanism include avalanche and the Zener tunneling. So, and you can see that in case of VI characteristics, whenever the semiconductor diode is in forward bias, no current flows until the barrier voltage is overcome. Then this VI characteristic curve has a linear rise, and the current increases with the increase in the forward voltage like ordinary conductor. And above 3 volts, majority carriers passing the junction gain sufficient kinetic energy. So, and these majority carriers, they hit the other atoms, and they knock out the valence electron, and therefore the number of valence electron increases, So therefore the forward current increases sharply here, whereas we have seen that whenever the semiconductor diode is reverse bias, you can see that a potential barrier at the junction is increased, and junction resistance increases and prevents current flow. However, the minority carriers are accelerated by the reverse voltage, resulting a very small current, that is called as reverse current, which is in the order of microamperes here. So therefore if the reverse voltage is increased beyond a certain value called as breakdown voltage, then the reverse current increases sharply here, and the diode shows almost zero resistance, and this is known as the avalanche breakdown here. So therefore reverse voltage above 25 volts destroys the junction permanently here. And also we have seen the VI characteristics of the PN semiconductor diode under forward bias condition is represented by I equal to Is into e raised to V by N Vt minus 1, where Is is called as the saturation current, Vt is called as the thermal voltage, whereas N usually it will have either 1 or 2, but in general it will be the number N will be equal to the 1 here. And also we have seen that the turn on voltage, it depends, it varies depending upon the material that is being used. In case of the silicon, the turn on voltage or threshold voltage, whatever we say, that is 0.7 volts, whereas for germanium it is only 0.2 volts. So therefore diodes with different current rating will exhibit the turn on voltage at different currents here. So, and also we have seen the few diode parameters we have defined. One is called as the VR, that is the maximum reverse DC voltage that can be applied across the diode here, and also we have defined one more parameter called as IR, the maximum current when diode is reverse bias with a DC voltage here. Similarly, we have one more parameter called as the IF, which is defined as the maximum average value of the rectified forward current, whereas FM is called as the maximum operating frequency of the diode here. And finally, we have also discussed about 3 approximations of a diode, wherein in first approximation the diode is represented by either open switch or closed switch. In second approximation, the diode is represented by the switch in series with a 0.7 volts battery, whereas in third approximation the diode is represented by the switch in series with 0.7 volts in series with RB there. So depending upon the application, the diode can be modeled in one of these three the approximation here. So in first approximation you can see that if the diode is forward biased, the switch is closed and the diode behave as a conductor with a 0 ohm of resistance here. If the diode is reverse biased, the switch is open and the diode will behave as a open with infinite resistance there. Whereas in second approximation, so it requires 0.7 volts of forward bias to overcome the barrier potential. Therefore, whenever the semiconductor diode is forward bias, in second approximation it is represented by a closed switch in series with 0.7 volts voltage the battery here. So whereas when the diode is reverse bias, it is represented by open switch in series with the 0.7 volts diode drop. So whenever the diode is forward bias, the current flows. When it is reverse bias, no current flows because the diode is represented by the open switch here. Finally, the third approximation requires or includes so both the 0.7 volts barrier potential and internal resistance of the diode, that is called as the bulk resistance. Therefore, whenever the semiconductor diode is forward bias, it is represented by a closed switch in series with 0.7 volts in series with the RB there. Whereas the when semiconductor diode is reverse bias, it is represented by the open switch in series with 0.7 volts which is once again in series with the RB here. So finally we had a discussion with this when are these different approximations are being used. In case of first approximation, as I told you that this is being primarily used in troubleshooting, that is mainly to know whether the diode is conducting or not. Whereas the second approximation is being used whenever a more accurate determination of the load current and load voltage required. Whereas the third approximation of the diode, it is being used during original design of the diode circuit there.